Okay, I have started the recording. This is the session for week 5 NPTEL course E115 for 2023. Okay, Venkata Subbareddy, go ask your question. Yeah, a 2-bit full adder, yes. Uh, Not using one, no. Hmm, hmm. You can't use only one adder. You'll have to use 4 adders. You will have to use 4 adders in series. Uh, uh, why not? So, that is only for one full adder. If you use 4 full adders, you have 12 inputs, right? And you have 4 outputs. Hmm. Hmm. Okay. Hmm. Okay. uh, you will just have to use more and more adders and more combination circuits to get the carry. Hmm. Which yeah, if you have four digit numbers, you can't do that. You can only add two 4-digit numbers. Ah. Ah. You'll have to use. You'll have to use more. You will get a the circuit for two numbers is shown in the lecture, right? Uh, and then you'll have to use two of those. You'll have to use three of those, I guess. No, for you'll add A B with one adder. You'll add C and D with one adder, and the results both of them you'll add with another adder. You will need three adders. Four full adders. Only four full adders? No, four 4-bit adders. Why you don't need four? Oh, you need at the same time, is it? Ah, but even then, how will you do it? Yeah, you'll have to design another adder for that. You'll have to design your own adder. See, this adder was also built with and gates and NOR gates and AND gates. Only these things, right? So you write down the truth table and use a K map and minimize it, and whatever you get, you make a circuit that can add three numbers or four numbers. You can do it. Wait, I'll open that PDF. I'll see. This is a carry liquidator. Was that week 4 then? This one, this is what you're talking about, right? Yeah. Ah, see, but this is the full ladder, right? You construct your own full ladder that can add 3 bits at a time with a carry. Here they have only added 2 bits x and y, right? And one carry z is there. Similar to this, you can make your own circuit that can add 3 or 4 bits x, y, z, w. Ah, you must write this truth table. Here they have written for 2 bits, right? 2 bit input. Yeah, you have to write the table for those many number of inputs and write the k-map, minimize it, and uh, you have this function here, right? 1 minute. This thing is what they've implemented, right? Uh, this here, and this is the sum. That's the circuit that they have given here. Similarly, you'll get another circuit for 3-bit adder. And using 4 3-bit full adders, you can add 3 4-bit numbers, right? Yeah, you'll have to do that. Not using only this full adder, you can't do it simultaneously. You'll have to do it one by one. You'll have to add A and B, then to the result, you'll have to add the sum of C and D, or you can add one by one. No, is there any? Hmm. You send me the question, the chat. I'll see. No, whatever exact question that sent you, send me a picture. Or you tell me which paper, which question it was, which year paper. Okay. I'll continue with my uh, problem solving. Is that fine? You can send it later, or you can ask that next class, or at the end. Yeah, whenever you find it, you can send it, and then I'll continue with this because other students are waiting, right? Okay. Uh, First question: find the number of 2:1 mux required to implement a 16:1 mux. Amit Kumar has said the answer is 9. 15, How do you do it with 9, Amit Kumar? Ah, okay. You're saying 15, but Amit Kumar said 9, so he must have some idea, right? Let him tell. Amit Kumar, you can unmute yourself, and are you there? you have some idea, you can tell. Well, I don't think you can do it with 9. If you can do it, then please share. Uh, like you said, you have to do it with 15. Why is it 15? How is it 15, Venkata? What is it? Yeah. Yeah, 16, you have to divide by 2, you'll get 8. Then 8 by 2, you'll get 4, you have to add. Then 2 plus 1, 15. Okay. Yeah, that is with 2 is to 1. What will you do if they give you 4 is to 1? Yeah, you use the same formula, no? 4 and 4 by 4 is 1. You add 1. 4 plus 1, 5. But how did you get this formula? Okay, okay, but what is where is the circuit for that? What if they ask you to show? Uh, yeah. So you can have multiple stages of multiplexers to select the line. So basically, a multiplexer, you have a select line. Yes, if it's 2 is to 1, then you have two lines. This, let's say, side 0 is I1. If S you give it as 0, you should give output as I0, whatever it is. If I0 is 0, you will get 0. If I0 is 1, you will get 1. Similarly, if S is equal to 1, you will get I1, whatever it is. Right? Okay. Okay. If S is equal to 1, you will get I1 here as the output. So if I1 is 0, you will get 0. I1 is 1, you will get 1. That's the 2 is to 1 multiplexer. So this has one select line, two inputs and one output. So if you want 16 inputs, at least you must have a minimum of 8 2 is to 1 multiplexers, right, to get 16 lines as input. Okay. Then you give your inputs here. I0, I1, I2, I3, I4, I5, I7, I8, I9, 10, 11, 12, 13, whatever, more, 14, 15. And what you do is you give the select line to all these multiplexers as S0. So if S0 is 0, it will select the lines above. That is, it will select I0, I2, I4, I6, I8, I10, the even numbered lines. And if S0 is 1, it will select the odd numbered lines. Take these and feed it to every two of them, feed it to a 2:1 multiplexer. Like this. And for each of these, the select line you will give so again you take two of these and one max, and then select line will be S2. Finally, this is S3. So this will be your 16:1 max. As you can see, in the first stage you have used 8, 16 divided by 2. Then you have used 4, then 2, and 1. So the total is 15. Suppose, let's say, in the second stage, instead of using 2:1 mux, you had an 8:1 mux. Then you could simply use that one, a 8:1 mux. So you need only 9 multiplexers. Well, is there anyone who hasn't understood how this works? Well, it's simple. If you write down the truth table, S3, S2, S1 is 0. For 0, 0, 0, 0, you need to select only line I0. This should go, or this should be sent as your output. 0, 0, 0, 1, you should set I1, right? If you make a table like this, and you can see that this, whenever S0, S1, S2, it will send the top line here. So when S0 is 0, it will send this, that's I0. And when S1 is 0, this multiplexer will send whatever comes in at this line. So I0 will come here. If S2 is also 0, then this I0 will come in this line. And then if S3 is also 0, the same thing will be sent here. If you see the truth table, you could try with a smaller combination. You could try an 8:1 mux with the 2:2 with several 2:1 muxes and see how it works out. You can write the truth table and check. Okay. Try to solve this one. You can type your answers in the chat if you are able to solve it. Okay. So this multiplexer, for a multiplexer, if you want to write the output expression in terms of the input variables and the select variable, so if I0 and I1 are the input, select as S and Y is the output, let's say, and Y is S0, S bar I0. That is, when S is 0, S bar will be 1, right? So at that time you have to select I0 plus S I1. So when S is 1, S bar is 0, so this first term becomes 0, and the second term becomes 1 into I1. So it is nothing but I1. So when S is high, the second term is selected, so we'll get I1 at the output. When S is low, the first term is selected, so we'll get I0 at the output. So this is the output expression for a multiplexer. And as you can see here, I0 is Y for the first multiplexer, and I1 is 0. So what you get here is X bar Y plus X into 0 is nothing but 0. So you get X bar Y, and then that is inverted. So we'll get X plus Y bar here as the input. Now you can think of this as I0 and I1 for the second multiplexer, and you will get F is equal to Z bar X bar Y plus Z into X plus Y bar, which is Z bar X bar Y plus ZX plus ZY bar, which is option B. Here the answer is option A. Okay, what about this one? D. Why is it D? Hmm. 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 Well, okay. See, one thing to notice here is they have given select lines as S1 and S2, but usually select lines will be S1, S0, right? So S1 will be the MSB and S0 will be the LSB. But the thing here is this S2, even though the 2 is a higher subscript, that's not the MSB, that's the LSB for this question. I don't know why they have given this notation, but yeah, nothing we can do about it. So we will take this as MSB and this is LSB. So when AB is when A and B are 0 and 0, this I0 line is selected. So when A and B are 0 0, that means A bar B bar will be high. At that time C is selected. So output will be A bar B bar C. And similarly when AB is 0 1, so you get A B bar A bar B is high, and again that will select I1, which is also connected to C. So it's A bar B C plus when AB is 2, that is when A B bar is high. So uh, 2, I mean by 2 I mean 1 0. This combination is given to the select lines. You can see A is 1, B is 0, so B bar is 1. So A B bar will be 1. And since at that time the output will be whatever is given to I2, which is C bar. And finally, when both the select lines are high, you will get I3, which is nothing but C bar. This is the output Z. You can simplify this A bar C into B bar plus B, the first two terms. Next two terms will be AC bar into B bar plus B. So you will get A bar C B bar plus B is 1. So, and A bar C into 1 is A bar C. This is not but A XOR C. Okay, question number 4. What function is performed by the circuit given? 4 is to 1 mux. Okay, there are 4 inputs, 2 select lines. So if it was a mux, it would be 4 is to 1. If you want to verify the operation that has been performed, you can see the first mux is connected to S1. So this is S1. This is also S1. This is S0. I had previously shown you the output expression for a 2S1 multiplexer. S bar I0 plus SI1. So here it will be the um, let's call it A and let's call this B. B is nothing but S2 plus S1 I3. B is nothing but S1 bar I0 plus S1 I1, and the output F is S0A plus S0 bar B. Now we plug in the values of A. S0 bar into S1 bar I0 plus S1 I1. You will get S0 S1 I3 plus S0 S1 bar I2 plus S0 bar S1 I1 plus S0 bar S1 bar I0. So if you try to write kind of a truth table for S0, S1 and F. If both are 0, only this term is high. So you will get I0. This will be 1 if both are 0. If it's 0, 1, you will get I1. From only this term will be 1. So for 0, 1, this will be 1. So 1 into I1 will be I1. Similarly, for 1, 0, you will get I2 and 1, 1 will get I3. So it is a 4:1 mix. Any doubts? No doubts. Okay. 5:32 decoder circuit can be implemented with A. How will you do it? Hmm. Yeah. You could have one decoder like this and four decoders after that in the next stage. So 2:4. There will be four lines, right? Each of those lines will be used and enabled for. These are enable. Here enable will be. If it's active high, then enable will be 1. Suppose you have a bubble here, then you will connect it to ground. Venkata, can you mute your mic? Okay. And then what you do? 5:32 decoder. So if you give a 5, you need 5 inputs A, B, C, D, E, let's say, and it should select one output line depending on which input combination you are giving. So if you give 0000, a line called O0 should go high and the rest of them should go low. So what you do is the first two variables you give here, and then the same CDE you give to all four decoders. So why does this work? How does it work? This is the circuit, but how do you know this actually works like a 5:32 decoder? Yeah. Hmm. Yeah, but why does it circuit actually work? Uh, the circuit is correct, but how do you know if you give the correct input, the correct line will be selected? You have the circuit. Okay, I'll give an input as 01100. Then what does it mean? This one. Yeah, this will be off. Off. But what about within this decoder? Ah, it's ah ah this 0, 01, 02, 03, 04. Yeah. Okay. Uh, yeah, that's right. If you look at the one useful trick here is if you look at the truth table for half the values, for the first half of values a will be 0 and the second half of values a will be 1. If you write all possible combinations of inputs that you can give, so there are 5 variables, there will be 32 combinations of zeros and ones that you can give as input. So when you write them in order, this order that we follow, the first half will have a is equal to 0 and the second half will have a is equal to 1. For b, the pattern is for every again you'll have to divide it into half, so you'll get 4 parts. So in the first part it will have only zeros, b. Second part it will have ones, again third part will have zeros, the fourth part will have ones. If you come from the right, you can see e changes every time, right, from one input to the next. So e changes from 0 to 1, then 1 to 0. It is flipping uh, when you go to the next input. D changes uh, in a different pattern. So you'll have two zeros and then two ones, and again two zeros, then you'll have two ones. C, it will have four zeros and four ones. So if you observe the pattern, you can kind of understand why this decoder circuit works. Is there someone who didn't understand? If you have a doubt, you can ask. Okay. How many 3 is to 8 line decoders with enable output are needed to construct a 6 is to 64 line decoder without using any other logic gates? How many do you need? We just did a question like this, right? 5 is to 32 decoder. Here we need a 6 is to 64 decoder. So there's one more variable, one more input variable. And again, here you had one 2 is to 4 decoder, but now you'll have to use only 3 is to 8 decoders. How many will you need? Well, you have 64 output lines, right? And a 6 is to 64 decoder. If you use 3 is to 8, then you need at least 8 at the output stage, right? To get 64 lines. So we'll have 8 blocks like this. And each of these will have 8 output lines. So that will make up 64 output lines that you need for the 6 is to 64 decoder. And each of them will have 3 input lines. So that will take up 3 out of these 6 input lines that you can use. So let's say you have A, B, C, D as the inputs, E, F. So you can give D, E, F here to each of them. And then similar to the previous question, here you had 2 is to 4, but instead if you had a 3 is to 8 decoder, then each of the 8 output lines could be used as the enable for these decoders, right? Like this. And if this would have 3 inputs, you could give this as ABC. This would turn these 3 is to 8 decoders into a 6 is to 64 decoder circuit. So you had 8 decoders in the output stage and 1 decoder in the previous stage. So you need a total of 9 stages, 9 decoders. Any doubt? Okay. To implement the multiplication of two 2-bit numbers, the following circuit components are required. How would you implement multiplication of two 2-bit numbers? Let's say my numbers are B1, B0 and A1, A0. When you multiply, how do you multiply? Normal, similar to normal decimal multiplication, you do A0, B0, A0, B1. Then you leave a gap here. And then A1, B0, A1, B1. And you add the terms in the same column. So for A0, B0 you need one AND gate. For A1, B0 you need one AND gate. A0, B1 and A1, B1 you need one AND gate each. So you need 4 AND gates. And then you have an addition here. For that you need one full adder. And that carry should be added to A1, B1. So you need one more full adder to add that carry. Or you could have used a half adder for this part also, but anyway, you don't have an option like that. So you need 4 AND gates and 2 full adders. That is option C. Venkata, yes, you can ask. That's your assignment question, right? I can't solve that. Okay. 13 question, right? Addition of three 4-bit numbers will be implemented by. Ah, full adders and half adder. You don't tell him the answer. For this, you will get. I can't really help you solve this question since it's an assignment question. I can help you solve it afterwards, after the assignment has been submitted. Hmm. Oh, okay, okay. Yeah, I don't know what they mean by 4-bit full adders. What do they mean by that? But one of them is a carry, right? You don't really say as you say 3-bit adder, full adder. You say 2-bit full adder only. You don't consider the carry as one of your inputs. Yeah, yeah. So you that full adder is called a 2-bit full adder only. 2-bit half adder and 2-bit full adder. Or no, no, one bit, right? A single full adder is called a one bit of two different numbers. So I don't know what they mean by 4-bit full adders. They have given 4-bit adder, right? 4-bit adder means no, in option B, C, and D, they haven't said 4-bit full adders. They have said 4-bit adders. So maybe the first option also they meant adders. I'm not sure. You'll have to ask in the discussion group that's here. There's an option called ask a question, right? Maybe try asking there what they mean by 4-bit full adder. Yeah. That this question I can't help. This 13 question I can't help you solve it. Even if I find out the answer, I can't tell you now, right now. So it's best you ask in the discussion forum, and then they'll tell you whatever hints they can give. Hopefully. Okay, you can ask your question. Who was it? Suresh. Suresh, is it? Yes, yes. Go ahead. Which one? Ah, ah. Hmm. You want a faster method, is it? Hmm. For this problem, I'm not sure. For multiplexer, there was this formula. Did you were you there during that time for the first question? So here, see, they've asked how to implement a 16 is to 1 mux using a 2 is to 1 mux, right? So you'll have to do it in. different stages, and in each stage number of multiplexer will be divided by 2 if you are using 2 is to 1. So if you are 16 inputs, you can give to 8 multiplexers, and then you'll get 8 outputs, right? In the next stage you'll have 4 multiplexers, so the total number of multiplexers will be 8 plus 4 plus 2 plus 1 at the end, right? So if you add one more stage, let's say they asked you 32 is to 1 mux, you would simply have 16 plus this number. Or suppose they gave you other multiplexers also, like 4 is to 1, 8 is to 1, whatever it is, depending on how many they gave you could use it in different stages. So let's say first stage you have to use only 2 is to 1 multiplexers, then you feed the 16 inputs to 8 of them. You will get 8 outputs. Let's say second stage and all, they don't give you any restrictions. Then you could simply use one 8 is to 1 multiplexer, right? Yeah, you could simply use one 8 is to 1 multiplexer, so the total number of muxes will be 9. Or if they gave you only 4 input multiplexers, you could divide this by 4 instead of 2. So first stage you'll have 16 by 4, that's 4. Next stage you'll have 4 by 4, that is 1, so you'll have 5. So for this mux question, this type of simplification is possible, but that is possible only because you have no other way of you have no enable inputs, and you can't give the input to a select line. You have to give the inputs that you have to the inputs of multiplexers only. So in each stage, you will have to use this fixed number of multiplexers. There's no other tricks you can use. But in this decoder question, then I am not sure if you can do it like that. So here in this question, they have 5 is to 32. 32 output lines means you need at least 4 3 is to 8 decoders, right? In the output stage. Yeah, and you have an enable also here. So you can use the enable and connect it to 1 2 is to 4. So it will become 5 inputs to 32 outputs. But here again, if you have a 3 is to 8, you can get with a similar structure, you can get 6 is to 64. So yeah, yeah, you need 64 lines, so you need at least 8 9 10. It can't be A, but the remaining things you can't really say. So you will have to think of the logic that you are trying to get in your head and try to do it. You don't need to write down the circuit all the time, but uh, no, there's no method like that. There's no fixed method for that type of thing. You will have to just practice more and more questions, and as you practice, you will just become better at it. You'll see a lot of problems, right? And when you're seeing a lot of problems, you see something similar to that, you'll know, okay, this type of simplification is possible. Other than that, there's no standard procedure. I'm not really sure. I don't think there's a direct method, the standard method that you can apply. Hmm. Yeah. I'm not sure how you do that. As far as I know, when they are trying to implement it in practice, they if it's small for small circuits, they'll just use this K-map and all. But if it's a huge circuit, then they don't do it manually. They just use software, Verilog or VHDL, whatever it is, and then they'll design circuits. At those times, they'll have just modules already present, right? So they don't go into the nitty gritty and deal with every single gate that they have. Yeah, yeah. For that, there's no common method. I know the standard method. You will just have to practice, and that's all. Most of the questions are like that. You'll have to practice and try to find some tricks. You can search in YouTube, right? They'll show tricks to solve certain types of questions. How to get to half adder? Shreya, can you clarify what you're asking? Oh, it's not half adder. No, no, no. It's full adder. Wait, wait a minute. It's half adder only, right? I'll explain 1 minute. Half adders. Yeah. Go ahead. Yeah, I'll explain that. Okay. Uh, Using AND gates, you'll get the four different terms. First stage: A0 B0, A0 B1, A1 B0, and A1 B1. And then what you do? This is your LSB. You give it directly. LSB. Then you have to add these two. So half adder, it has two inputs, right? It will give you a sum and carry, right? Uh, so XY, sum and carry. You will feed this A0 B1 here to one of the inputs, and A1 B0 will give given to the other input. Sum will give you A0 B1 plus A1 B0 or whatever it is. It will do XOR, right? So this is binary addition. Uh, this thing. That's not decimal addition. So you will get the sum here, you will get the carry, and then what you do is you feed this carry. This carry has to be added to A1 B1, right? So one more half adder you use, um, you will get sum and carry. So uh, whatever sum you get, this is the middle bit, and whatever sum you get here, this is the MSB. Is that fine? Okay. So you have four AND gates and two half adders. Huh. Full adder circuit. I didn't exactly understand your question. Can you share the question in the chat? If you have a picture of that question, you can if you can upload it, I'll see. I didn't understand exactly what you're asking. If you can see the circuit, maybe I'll understand. Uh, This is a full ladder, right? What's the problem? Vishwanathan. Huh. This one, Z. Huh. That's that's the difference between full adder and half adder, right? Half adder doesn't have a carry input. Full adder has a carry also. See, carry is will be your MSB. Actually, you're not supposed to consider carry as part of your number, but if you want to do it, carry will be your MSB. They have given a truth table here, right? X, Y, Z. So if you add 0, 0 and 0, it's your output should be 0, right? Oh, you're saying, see, there's no MSB, LSB here. It's just 3 bits being added. It's you can take whatever you want as your LSB and MSB. It won't matter. It's not weighted. It's not a weighted number. This 000 doesn't really mean you are giving a number 0 to the inputs. It simply means you want to add 0 and 0, and previously you had a carry of 0. That also you want to add. Hmm? Yeah, it's only XOR, right? It won't matter which order you add them. Okay, but what is your problem exactly? Is it? Hmm. I got even more confused now. Okay, I have sent you the email ID. You can mail that to me. You can mail your question. I'll see. Once you mail, you tell me. Okay. I'll see it right now. D. Okay. Why is it D? Yeah. Yeah. 7 segment display can only display from 0 to 9 if you have only one display. So uh, you can only decode from one BCD digit, one BCD number. So there are only four inputs. Okay. Add these two numbers in BCD. See, they're asking you to add it in BCD, but no one will come and tell you. No one can come and stop you if you add the decimal number. So you don't really need to add in BCD. You can simply add 96 plus 69. What is it? 165. What will this be in BCD? 165. as well, as long as there's no overflow or anything here. So this is the right answer. If you really want to do it in BCD, just to understand how to add, then 96 is 9 and 6. 69 is 6 and 9. First you simply add these 4 bits together. You'll get 1111, 1111. But suppose your addition exceeds 9, then you have to add another 6 to this. So you have to add 6 because this is 15, that is greater than 9, and again you have 15, that is also greater than 9. So you have to add 6 to this also. When you add that, you enter. Okay. Okay, after this I'll check. So what will this be? 1 1 plus 1 is 0 with 1 carry. 1 plus 1 plus 1 is 1 with 1 carry. 1 plus 1 is 0 with 1 carry. We'll leave the carry as it is. So these are the same addition, right? So this will also be 0 1 0 1, but we have a 1 carried over here. So you'll get 6 with 1 carry. It's the same thing. So if it's a subjective type question and you need to write down the answer properly, then you'll have to do in BCD. But if it's MCQ like this, then you don't really need to do it in BCD, right? You can simply do the decimal addition and write the BCD equivalent. Okay, I'll solve 2 more questions. These questions are from previous assignments, so solve 2 more questions and then I'll come to your doubt. Okay. BCD equivalent of 345. So for each digit you write 4 bits. That's all. Yeah, this is 3 is 0011, 4 is 0100, 5 is 0101. So it's D. And then A, you have 4 inputs I0, I1, I2, and I3, 2 outputs A and B, and the expression for the outputs are given. They're asking you what circuit that is. What circuit is it? Well, first thing is first, there are 2 outputs, right? So it can't be a 4:1 mux, right? It there's there doesn't seem to be anything related to BCD, so it's probably not BCD. Yeah, Dmux also. Mux Dmux is simply opposite, right? You have select lines here and you have inputs here and one output. Dmux will be the opposite of this, something like this, I think. You'll have 4, so you'll have more outputs than inputs in a Dmux. And there's nothing really about any select lines or anywhere here, so it's probably not a Dmux also. So just by elimination you can with high probability say that it's a priority encoder, but if you want to be sure, you can write out the truth table for it. What will the priority encoder do? I3, I2, I1, I0, A, B. So if this thing is high, regardless of what these are, its output should give you the number 3, which is 1 1. And if this is low and this is high, regardless of what these two are, it should give you a 2 1 0. And similarly this will be 0 1. Finally, If only I0 line is high, you should get 0 0. So you can see A is high only when I3 is high, or when I2 is high, then A will be high, right? So that's what you have here. And B will be high when I3 is high, or if I3 is not high, there's one more combination. I2 should be low and I1 should be high. So I2 bar I1. That's the thing you have. So it's a priority encoder. Any doubt in this question? For B, right? You're saying but it's okay. See, when I3 is high, it will be high anyway, right? So even if you include I3 bar, it doesn't make a difference, right? Or you could write it as I3 bar, I2 bar I1. It's nothing but I3 plus I3 bar into I3 plus I2 bar I1. So something but I3 plus I2 bar I1. Or even physically, if you check here, see, suppose you have 101x. What's the problem? I3 is 1 anyway, right? And I3 is 1, B is high. So it's not a problem. Suppose it doesn't have to be 001x. It can be 101x also. Suppose this B was not high for I3. Suppose here also it was 0. Then you would have to specify exactly for this. You would have to write I3 bar, I2, I1. But B is high when I3 is high anyway. So it's okay even if you omit this I3 bar here. Or if it's difficult to understand it physically, you can simply do the Boolean algebra and it will get reduced to I3 plus I2 bar I1. Okay, I'll see my mail now. Uh, is this a previous year question or is it from a mock test? Okay, let's see. How do I send it to? Oh, yeah. Doesn't work. Give me a minute. small part is cut off here. What does it say? 4 is to 1 multiplexer is to be used for generating the output sum of a full ladder. X and Y are the bits to be added, while P in is the carry input, P out is the output carry, and S out is the sum output. If X and Y are connected as select lines S1 and S0 of the multiplexer as shown below. Which one of the following statement correctly describe the choice of signals to be connected to the information lines I0, I1, I2 and I3? Full ladder we had what's the sum and carry in full ladder? X XOR Y XOR P in, right? And then what? For carry? XY plus Z into X XOR Y. Okay. P out is the output carry. Well, this question it's not dealing with P out, right? Only sum. Hmm. Yeah, this XOR and all. We don't really need the carry then. We needed only the sum. What is X XOR Y? X bar Y plus XY bar. XOR at P in. So this is P in bar plus P in into bar Y plus XY bar. That's all right. So this is complement. X bar Y P in bar plus XY bar P in bar plus P in into what will this come out as? XY plus X bar Y bar, right? It's X nar. XY plus P in X bar Y bar. XY is the select lines. X bar Y bar you give P in. X bar Y you give P in bar. XY bar you give P in bar. And XY you give P in. Which one is it? B, right? Did you understand? Huh. See, XY, that, let me explain. What does it mean to have a 4 is to 1 mux? This I0, I1, I2, I3. You have select lines S1, S0. The output, if you write it, okay, what you want to do is when S1, S0 is 0, 0, you want to select I0. When it's 0, 1, you want to select I1. When it is 1, 0, you want to select I2, and 1, 1, you want to select I3. So if you write the truth table for that, the expression that you get, or whichever way you can understand easily, the output, if you write the expression for the output, it will be S1, S0, I3 plus S1, S0 bar, I2 plus S1 bar, S0, I1 plus S1 bar, S0 bar, I0. This is the output of a multiplexer. Okay, you can get this. You can simply think of this. What happens when S1, S0 is 0, 0? This term will go to 0, 0 into 0. This is 0 into 1, this will go to 0. This is 0 again, this is 1 into 0. Right? S1 bar is 1, S0 is 0. So this will also go to 0. Because 0 times I3 is 0 only, right? 0 and I3, 0 and I2. Only this term, 0 bar is 1. So 1 and S0 is also 0, so S0 bar is 1. 1 and 1 and I0. So you get I0. Right? When it is 0, 1, you can check. Only this term, when the select lines are 0, 1, only this term will not vanish. All the other three will go to 0. Okay. Similarly, when, okay, wait a minute. Only when it is 0, 1, this term will not be 0. All the other terms are 0. And when it is 1, 0, this term is non-zero. All the other terms are 0. So, see, if you can see S1 is 1, so this is 1. S0 is 0, so S0 bar is 1. 1 and 1 and I2. So I2 will be your output. Similarly, if it's 1, 1, this is 1, this is 1, this is I3. So 1 and 1 and I3 will get. The other terms will become 0. So this is the expression for the output of the multiplexer. Okay. You can get this by writing out the truth table also. But this is easier to understand. So once you have this, what have they done in the question? X and Y they have given as the select lines. So S1 is equal to X according to them. Right? S1 is X, S0 is Y. That's what they've done. S1 is 0. So in this expression, wherever you have S1, you can replace it with X. Wherever you have S0, you can replace with Y. So what do you get? XY I3 plus XY bar I2 plus X bar Y I1 plus X bar Y bar I0. Okay. Then compare it with what you want. You want XY P in. So you have XY I3. So for I3 you have to give P in. You compare the other term. You have X bar Y bar P in. Here you have X bar Y bar I0. So your I0 must be P in. And X bar Y I1. So you have this term X bar Y P in bar. So your I1 should be P in bar. Similarly, the other thing will also be P in bar. Okay, that's how you solve this. Uh, uh. See, carry they have not considered carry only. P- output out. Huh. I didn't understand. Pin is the input that you are given. Pin is the input carrier, right? You already have that with you. Okay, you're saying where are you getting P in bar? Is that it? I didn't understand your question. Can you repeat it? Ah, see, this is P out, right? P out, where they have they asked P out? They don't have P out only. They ah they have this P out. See, in the beginning only I told, right. I wrote this expression, but then I told that it's not necessary because they have not asked P out. They have asked only S out. P out, they don't even care. Only to confuse us, they have given P out. Yeah, it's not being used. They need only the sum. See here, only S out is here. Where is P out? They didn't use it. Okay. Any other doubts regarding the topics that have been covered so far in the lectures? I have some more time, so I'll simply solve a few gate questions if no one has doubts. If you have doubts, you can ask and get them clarified now. Ah, you send me the problem. Okay. Wait 1 minute. You sent to this email ID. That one I have not added it to my tab. I sent you an email ID now. Send it to that. Anyone else has any questions? Vishwanathan, will you send now or should I wait for you? Okay. See, for the ring oscillator shown in figure 1.12, propagation delay of each inverter is 100 picosecond. What is the fundamental frequency of the oscillator output? Anybody has any idea how to solve this? Well, for those who don't know what whatever multi-vibrator you said, for those who don't know, what should they do? Is my video so blurry? But yeah, I took this question to explain how you are getting an oscillation, right? So let's say initially output was at 0. Okay, so this is at 0. Oh, what will happen is this output should be 1 and this should be 0. This should be 1, this should be 0, this should be 1 now. So there's a problem here. It can't be both 1 and 0 at the same time, right? So if this was an ideal circuit, it wouldn't really work. Something would have went wrong physically. But since there are delays, we can actually practically connect a circuit and make it work without any problems. as such. How that happens is once you set the output at 0, uh, this will only go to 1 after 100 picoseconds. So that effect is not felt by the output at that time because these gates have delays in their outputs. So after 100 picoseconds, uh, this 0 will propagate here and it will become a 1. So after 100 more picoseconds, this will go here and become a 0. In another 100 seconds, this will go to 1. One more 100 seconds, it will go to 0. So one more 100 seconds, it will go to 1. Then since this has become 1, now again the input is 1, so this will change to 0, this will change to 1, this will change to 0, this will change to 1, this will change to 0. Now again it has become 0. So it started out at 0, right? And then for about 500 picoseconds, it stayed at 0. And at 500 picoseconds, it will become 1. Because the effect of the 0 at the output will get reflected after 5 gate delays because there are 5 gates. Then it will stay at 1 for another 500 picoseconds, then again it will go low. So this is kind of a periodic signal. If you zoom out, it will look something like this. And this length is 100 picoseconds. This length is also 500 picoseconds. This length is also 500 picoseconds. The time period is the time between these 2 points, which will be 1000 picoseconds, which is nothing but 1000 into 10 power minus, how much is a pico? 12. So it's 10 power minus 9, and frequency is 1 hour time period, so it's 10 power 9 hertz. This is in seconds. This is nothing but 1 gigahertz. So actually if you connect inverter gates, I don't know what will happen, if it will actually work like this. And I'm not sure, I have not tried it myself, but theoretically if you think about it, this is what could happen. Okay, they have given us a circuit which contains an LED. What you everyone knows LEDs. So the property is LED is a light emitting diode. So the property of a diode is that when a positive voltage is applied, let's say if the voltage difference between these 2 points A and B, so VAB is greater than 0, then that LED will close the circuit and current will pass through it and it will emit light. But if point B is at a higher potential than point A, or if VAB is less than 0, then the LED is off and it won't emit any light. So they're asking for what combinations of these switches, S1 and S2. If you can either keep them off or you can close the switches. You can either open the switch or close the switch. So for what combinations of the switches will this LED glow? What do you think? This is 5 volts. No, yeah, this should be a 0 volt. So its output of this circuit should be logic low. 0, right? XOR gate. You don't know that, right? Oh, there's a connection here. Uh, this place. Huh? Yeah. How about we try connecting these switches and we'll see. Oh, yeah. You're saying S1 is closed and S2 are closed. So this will be at 0 volts. This will also be at 0 volts. So it will be 0. And whatever this output is, it will be 1. 1 in logic 1 is 5 volts. We are assuming it's 5 volts. That could be higher or lower. But since they are not specified, we'll take that as 5 volts. So both ends are at 5 volts. There's no potential difference. So LED won't glow. That's one case. And both are closed. But as you saw here, even if one of them is closed, one of the inputs will be 0, right? If S1 is closed, let's say we can call this as the input A to the AND gate and input B. If S1 is closed, A will be at 0. If S2 is closed, B will be at 0. Right? So if any one of them is closed, the input to one of the inputs to the AND gate will be 0. So again the same situation will happen. So again the LED won't glow. So you have to keep both of them open. Let's see what will happen if they are both open. The both of them are open, then this will be at 5 volts and this will be at 5. So this will produce a 0. Now again this will go high. So it is 5 volts. So again the LED is off. So none of the input combinations for the switches will give you light. So the diode doesn't emit light irrespective of switch positions. Okay. Any doubt? Or if you think this is wrong, you can tell me. Makes sense, right? Okay. Did you send me an email? Who was it? Vishwanathan. Okay. Okay. Video transmission system transmits 625 picture frames per second. 625 FPS frames per second. Each frame consists of a 400 by 400 pixel grid. 400 into 400 pixels per frame. Could write this frames per second. With 64 intensity levels per pixel. 64 per pixel levels. The data rate of the system is in bits. How do you solve this? Why 8? First of all, they have given 64 levels, intensity levels per pixel. They are not given in terms of bits. So if you have 64 levels, how many bits will you need to represent that? You need 6 bits, right? With 6 bits, you can have 2 power 6, 64 combinations. For each combination, you can assign an intensity level. You can't really send something called an intensity level directly, right? How will you send it? You're sending it in terms of bits. How many bits will you need to encode those levels? So this 64 levels per pixel would translate to 6 bits per pixel. Because with 6 bits you'll have 2 per 6 or 64 combinations, and each combination you can map to one level. So the number of bits will be in total, multiply all this feet per second, your frames per second, to 400 into 400 pixels per frame, and these frames get cancelled out, into 6 bits per pixels. These pixels get cancelled out. What you are left with is in bits per second. And if you do the multiplication, it will be how much? 6 into 10 power 600 into 10 power 6 bits per second, which is actually supposed to be 6 into 10 power 6 divided by 6 into 10 power 6 divided by 1024 into 1024 megabits per second, which is actually 572 megabits per second. But here, well, they are not talking about the digital mega term. They've simply taken mega to be 10 power 6. So it's 600 Mbps. But actually, it should have been 572 since we are doing digital electronics. Okay. Uh, so where am I looking? Let's see. Y is w bar x bar into y plus z. Implement using NAND gates. No? NOR. But the question says NAND. Oh, you want NOR. Okay. W x y z. It's 4 input, right? Uh, what are we supposed to do? You'll have to take POS form, right? You can't do sum of products. You have to do product of sums. Let's take it as W x y z 0001 1011 0001 11. Uh, hmm. Hmm. you'll have a lot of gates, right? Okay, okay. If it's just implement, if they have not asked you to minimize, then yeah, directly you can do it. Yeah, they have not asked minimum number of NOR gates, so you can do it however you want. Yeah, then you can simply use an NOR gate to get W bar, right? It will give you W bar. So you do the same with uh, X, you'll get X bar. Then you take W bar or X bar, you put it to a NOR gate. What will you get? You'll get W bar plus X bar, whole bar. Uh, W bar plus X bar and Y plus Z is nothing but W bar plus X bar whole bar plus Y plus Z whole bar complement, right? So you have this W bar plus X bar from this NOR gate. You can get Y plus Z bar from another NOR gate. You give Y and Z, you will get Y plus Z. And these two things you take, put it into another NOR gate. That will give you the output Y. Is that alright, Vishwanathan? That is NOR gate only, no? Are there any options that you have to choose from, or you just need to implement it? Then you can do it in this way. I'll write it more cleanly. Uh, you take W, give it to a NOR gate. You'll get W bar. You take X, give it to another NOR gate. Write X bar. You take these two, give it to another NOR gate. Get W bar plus X bar, all complement. Then Y and Z you give to another NOR gate. You'll get Y plus Z complement. And then you take these two things and put through another NOR gate. What will you get? You get plus W bar plus X bar complement plus Y plus Z Y bar. This is complement. And by De Morgan's law, this will be nothing but W bar plus X bar into Y plus Z. Right? I don't know if if this is the minimum, but this is one implementation that will work. That is correct. Okay. Any more questions? Huh. No, there's no, there's no formula. I don't know any formula. If you find out, you tell me. I'll tell the others also. But yeah, because there can be different tricks that you can use. This only worked because the expression was designed this way. If they had given a complement here, I would have to use one more NOR gate to get the complement of this. Or if instead of this they had used Y bar, then again for Y bar I would have to use another NOR gate. So there's no general standard formula for doing these things. You just practice and you'll get it. That's all. See, for this type of thing, you can't really do it with one gate, right? At least for For some complements will be there, some addition, multiplication, some one or two operations will be there. So if there are options like one gate or two gates, it's probably not possible if you have so many variables. So if there's something like three gates, maybe then you would have to simplify and see. But if the options are 1, 2, 4, and 6, then you're probably safe with marking 4. You can't really get just one gate, right? Even two gates doesn't seem to work. Maybe 3, but I don't think 3 also works. And that's how you check. Depending on options, if the options were just 4, 5, 6, 7, then you wouldn't even have to think. You could just mark 4. Any other doubts? See, for example, there's this question. Functions w, x, y, and z are as follows. Then, if you look at it, it looks a bit complicated, right? So you could uh, try to minimize the expressions and check if the options are telling you w is equal to z, w is equal to z bar. Those are the options. W equals y. So you will have to simplify all these terms to look similar to each other, and whichever of them are resembling after simplification, then you can mark that option. But doing that could be tedious in this case. In those times, one thing you can try is just give some input values and see what is happening. Suppose you give r is equal to 0, you give 0 to all these things, right? See, w can be equal to z, or it can be equal to z bar. It can't be both of them at the same time, right? So if you give this combination, at least some of these options you might be able to, one of these options you can eliminate, right? By checking the value of w and z. What will w be equal to? 0 plus other term also has 0. Everything will become 0. So it's 0. Now you check y. What is y? Or you write down x also. X. See, the second term, first term will go to 0 in x, and third term will also go to 0, because there is p in both the terms, and p is 0. But the third term, but the middle term has a complemented form of all the inputs. So everything will become 1, 1, 1, 1. So you'll get x is equal to 1. So from this, you can see w is not equal to x. So if there was an option that had w is equal to x, you could eliminate that from this. Since there is no option like that, it's fine for now. Let's check y. Again, the first term rs goes to 0. Next, it's 0 plus complement of pr is 0, pq bar is 0, p bar q bar is 1. So what is it? 0 plus 0, 1 bar is 0. So this will go to 0. And z you check. 0 plus 0 plus complement of pq is 0, p bar q bar r bar is 1. Next term is also 0. So it is 0. See, w is 0 and z is 0. So z bar will be 1. So w is equal to y is equal to z bar. This option is wrong. Right? It can't be true. Then from this x is 1 and y is 0. So x is equal to y can't be true. So it should be one of the other two options. Now just from this, you can't really tell which one it is. So you could try giving another input combination. Let's try p is 0, q is 0, r is 0, s is 1. So what will happen to w? S is 1 and rest are 0. So R bar S, this will be 1 and 1. So it will go to 1. Right. And since we have eliminated, we have only two options, w equals z and w equals y, we don't care about x anymore. We can just check what is the value of y and z. Maybe, hopefully, we will be able to eliminate one of these options. Let's see what is y and what is z. Y is rs is 0, pr is 0, pq bar is 0, p bar q bar is 1, y is again 0. Right. PR, PQ bar, P bar Q bar is 1. Yeah, so as you can see, W is 1, Y is 0, so W is equal to Y is also wrong. So this is the right answer. In this way, for some questions, it's easier to simply plug in values and check whether it is correct or not. If you try to simplify this expression, maybe you would be able to do it. I don't know, but maybe you won't be able to do it properly. Any question? Okay. Do you guys want to continue, or do you guys want to leave? Okay. Whoever wants to leave can leave now. If you have some other work, you can go. It's no problem. 2 hour session you attended. And anyway, there's no attendance, so you can leave in the middle whenever you want. But if there are a few students who stay, then I'll keep doing a few more problems. Okay, 4-bit 2's complement representation of a number is 100. What is the number? This you can simply tell. You don't no need to work it out. What's this number? It's not 0. See, there's a 1 right in the MSB. So it should be a negative number, right? Is it minus 7? 7 will be 0, 1, 1, 1, right? 1's complement will be 1000. 2's complement will be 1001. So it's not minus 7. Yeah, Dr. Vijay Kumar has given the right answer. It's minus 8. See, with 4 bits, you can actually represent only from minus 8 to plus 7. So this number is not plus 8. Well, you just take it as plus 8 for now and do the 2's complement with that. What will you get? You'll get 8 back again. So in this group, minus 8, this actually represents minus 8. And it's a complement of itself. So if you do 2's complement, you get back the same number. Next, they have a cascade of XOR gates. And they have given you there are 20 stages like this. So what will be the output function? For the first stage, you can see you have X here, you have 1. So what will be the output for the first stage? X bar 1 plus x1 bar, right? X1 bar is x0, which is 0. So it's x bar. That's for one stage. So for the next stage, x bar is input, and again the bottom input is x. See that x is going to one of the inputs of each of these gates here. This x, this x, this x. So you have x bar and x. So what is x bar XORed with x? It's 1. Now you can look at this part and see that it is similar to how we ended out. How we started out. We started out with 1 as the input and x as the other input to the XOR gate, and we got an x bar. So again we'll get an X bar. Since X bar is the input of the next stage, again this will follow the pattern for this second part. So in essence what will happen is, after one stage you will get if you just have one stage you'll get X bar. After two stages you'll get back one. In three stages you'll get X bar. In four stages you'll get back one. So if you had an odd number of stages you'll get back X bar. If you have an even number of stages you'll get 1. Is that right? X bar with 1 X bar 1. So they have given 20 XOR gates, so you should get 1. Was that correct? Was there any mistake? Okay. They have given an input Vi, which is initially it's at 0 and time t is equal to t0 it will go to high, logic 1, and I've asked you what will be the output waveform. The output is here V0. So what is the waveform of V0? And they have given delays for each of these gates. G1 is a NOR gate with a delay of 10 nanoseconds. G2 is an XOR gate with a delay of 20 nanoseconds. So which one will be the output waveform? For this you could write out the output at each stage. Here you are given Vi, right? This is the input that is given. So here you will get a Vi bar, and this is Vi, this is Vi bar. What is it? When you XOR you should get 1. You should get 1 if there is no delay. Since there are delay, you will have to write down the waveforms and then check what will happen. So this is input, T0, and for the G1 there's a 10 nanosecond delay. So they are not specified here, but we are assuming this distance is 10 nanoseconds each of them. So at the output of G1 you should get what? You should get Vi bar. That is, should initially be at high, and then it should go low, but after 10 nanoseconds. So that's what you get here. And then okay, Then we have to do XOR. So this is 0, this is 1, 0 XOR 1. Initially it will be at 1. Then this uh, V0 changes to 1, but V in changes to 1, but V in bar doesn't actually change for 10 nanoseconds. So uh, you will get an output 0, but this thing itself will get delayed by 20 nanoseconds. So the output should go to 0 after 20 nanoseconds. Then here everything is normal again. So this is 1 and this is 0. XOR will go high, but again this dip in the value will also get delayed by 20 nanoseconds. So it will go high after 20 nanoseconds. So it should be like this. So before T0 it's 1, it's option B if you compare. Any questions? This is T0. This thing is T1. This is T2. This is T3. Okay. N-type silicon is obtained by doping silicon doping. There was a in one of the Amit. Which one do you want me to repeat? This question. Uh, Let me add a page and do it in another page. So they have given the input. This is Vi. It's initially at 1. No, it's initially at 0. If you take this as 1 and this is 0, it's initially 0. And at this time, T0, it becomes 1 and stays 1 for the rest of the time. Okay. Now this input is given to gate G1. G1 is an inverter. You see, G1 is a NOR gate connected to the same input. So Vi is connected here. So Vi plus Vi bar, which is nothing but Vi bar, because A plus A is equal to A in Boolean logic. So you have Vi bar as the output of G1. But the thing is, so initially since Vi is 0, Vi bar will be high, right? And at T0, Vi goes to high. So Vi bar should go low. But the thing is, there's a delay in the output of gate 1, and that delay is equal to 10 nanoseconds they've given here. So after 10 nanoseconds, this change is reflected. So it should have went low like this, but unfortunately there's a delay. So it will go low after 10 nanoseconds. So this is the waveform for Vi bar. And if you look at gate G2, one of the inputs is directly Vi. This Vi, it's fed here. So this is Vi. And the other input to the XOR gate is Vi bar. That is the complement of Vi. So an XOR gate, what will it do if Vi is 0 and Vi bar is 1? So if one of the inputs is 0, the other input is 1, it should be at 1, right? So before time 0, it will be at 1. After T0, see the inputs both become high to the XOR gate, to gate G2. So when both of the inputs are high, the output should be low. But the G2 gate has a delay of 20 nanoseconds. So it was supposed to go low right here, but it got delayed by 20 nanoseconds. So since I said this is 10 nanoseconds, we're taking this as T1, another 10 nanoseconds, let's say this is T2. So it will stay like this and go low at this point. So it was supposed to go low here at this place, but there's a delay of 20 nanoseconds, so it's going low at T2. Then it will stay like that for the next 10 nanoseconds. For this 10 nanoseconds, both the inputs are high. Then after T1, Vi bar actually goes low because finally the gate 1 has given the proper output. Now again this is 1 and this is 0. So from this point Vi is 1 and Vi bar is 0. So the XOR should again give you a high output. But again, this change, it won't reflect at exactly this point. It will get delayed by 20 nanoseconds. So at this point, you are supposed to get high, but after 20 nanoseconds, it will be reflected. So at this time instant, say, it will actually go high. But before that, since it was 0, it will continue to stay in this 0 state. Okay, this is T3. If you compare the waveforms, it will be option B. Any specific doubt, or did you understand? Okay. N-type silicon is obtained by doping silicon with phosphorus, I guess. You'll get P-type by doping with boron. Because this has 5 valence electrons, if you look at the periodic table. And this has 3. Whichever has 5 valence electrons, it will donate an electron, so you'll get an N-type silicon, where there are more electrons than holes. And boron, it has only 3, so it will actually take away 1 electron in a sense from the silicon, so there are more holes, or which effectively act like positive charges, so we call it p type. Okay, the number of distinct boolean expression of 4 variables, how do we find this out? 16. There are 16 min terms, right? But each of those min terms can again be 0 or 1. By here, by boolean expression, they don't mean one single term. They mean a function, a boolean function. So it could have any number of terms. So if there are 4 variables a, b, c, d, then when you write out so let's say you form some function f. We don't know what that function is, but whatever it is, for each input value, it should have some output. It should either be 0 or 1, right? So there are 16 such combinations, 0, 0, 0, 1, 16 such inputs that you can give up to 1, 1, 1, 1. And for each of them, you can have the output as 0 or 1. So each of those combinations of zeros and ones that you give to f will lead to a Boolean expression. Yeah. So it's using the multiplication principle. If you say f is, say, sum of products from sigma of different min terms, 0, 1 up to 15. In this expression, either 0 can be included or it cannot be included. There are two possibilities. Similarly, 1 can be included or 1 can be discarded. There are again two possibilities. And the same for 16. So there are 2 power 16 ways of forming distinct sum of product expressions. That is 65536. Okay, we solved this. Range of signed decimal numbers that can be represented by 6 bit should be bit. One's complement number is, so one's complement you can go from minus 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. And just from this you can see these are just negative of each other, these two. So it should be something of the form minus 31 to plus 31 or minus 64 to plus 64. But you can see from the other options that they have different positive and negative values. So all of these are wrong. So you don't even need to calculate what number it is. You can directly say it's minus 31 to plus 31. But if you put n is equal to 6, you will see that it's 2 power 5 minus 1 to plus 2 power 5 plus 1. This is minus 31 to plus 31. Well, this one's complement is nothing but you have for 6 bits, let's say from 00000, you will go up to 111111, right? So about halfway there, about 31, you will stop counting in the positive direction and you will start counting in the negative direction. So whatever combination you had for 32 in your normal binary representation, that you will assign to minus 1, and then 33 you will assign to minus 2. Something like this will happen. So you will get negative numbers up to minus 31. In which order happens, it will be different in different systems. Of course, you can make your own system of assigning these numbers. There's these one's complement and two's complement numbers, they are not really weighted as such. You can't simply multiply out the weights and get your answer. So you can give any combination to anything. You can map them however you want. But this particular one's complement and two's complement gives you a rule that you can do, and that is also useful for computations. Okay. They have given 3 numbers and they're asking what these numbers would be. They're in 2's complement form, so in decimal, in signed decimal form, what will they be? So you can see from the first bit of each number, if the first bit is 1, that's a negative number, as long as it's a valid number. So they should represent negative numbers. And you actually do 2's complement operation on these numbers itself, and you should get the positive value of that number. So 1101, if you do 1's complement, it will be 0010. If you add 11001, so it's 00110. You add 1 to it, you will get 00111. So the 2's complement of this number is plus 7, so this number is actually minus 7. And from this, if you're writing the gate exam, then you shouldn't continue doing the 2's complement of the other numbers. You should see from the options that only this one has minus 7 in it, option C, and simply mark it and move on to the next question. But if it's a subjective type of question, then you'll have to do it for all the 3 numbers. So 1's complement is this, plus 1 is 0111, which is minus 7 again, and 2's complement 1 again, it's, yeah. So all 3 are minus 7. Okay. You have a Boolean function f of 2 variables x and y. is defined as f of 0 0 is equal to f of 0 1 is equal to f of 1 1 equals 1 and f of 1 0 is 0. Assuming complements of f x and y are not available. So if you want to get x bar and y bar, you have to use a gate to get it. A minimum cost solution for realizing f using only two input NOR gates and two input OR gates. So first we would have to get the expression to see how many gates we need. You can draw a simple table. You could draw a two table or you could draw a K-map, but will be the same. But you can minimize if you draw the K-map. X bar x and y bar y. 0 0 it's 1, 0 1 it's 1, 1 1 it's 1, 1 0 it's 0. So you can group these two and these two. So f is x bar plus y. And to get the inversion of x or x bar, you can use one NOR gate, two input NOR gate. You can just connect it like this. It will give you x bar. Or instead, and then you have OR gates also. So you can use two input OR gates also. You simply OR this with y. You'll get x bar or y. So you could do it with 2 units. And since one term is complemented and one is uncomplemented, then there's no possibility of doing this, getting this expression with a single gate. This is the minimum. Next question. Huh? Huh? Delay they have not asked. They've asked total cost of the minimum cost. They're saying yeah. So they're saying how many gates are used. That's all, not the delay. Yeah. Um, okay. Next, it's very simple. AC plus BC bar. So if you see, this is AC BC bar and extra term A bar C. So it's probably not that, right? There's an extra term, so it's not this. Similarly, AC B C bar, there are extra terms. This will simplify to C B bar. This will probably not go away, right? It'll give you some extra unwanted term anyway. It doesn't look like it'll become one. And you can look at option B. You have B bar C AC. You have BC bar plus A bar C B bar. Again, this doesn't look like this will go anywhere. It was just adding extra terms to your expression. So there are probably other input combinations that will give you one. A final option, if you see, this looks similar to a canonical SOP form. So you try to write out the canonical SOP of this term. It will be A B C plus A B bar C plus B C bar A B C bar plus A bar B C bar. And if you check, you have A B C, you have A bar B C bar, this one. Then you have A B C bar. And this one should have been A B bar C. They made a printing mistake, so A B bar C. So if this type of printing mistake happens, they will simply give you grace marks. There's nothing you can do about it. Okay. Decimal 43 in hexadecimal and BCD number system. For BCD, it's very simple. You just write 4 and 3 in binary separately. So This has 4 3. Option A has 4 and 3, and this is 4 and 3. This is 4 and 4, so it's not D. Um, and this option C has 3 and 4, so it's not option C. Now among option A and B I have to select 43 in hexadecimal. How much would it be? So the first bit has a weight of 1, and second digit has a weight of 16. 16 twos are 32, plus to get 43 you need to add another 11. 11 is nothing but B. So 2B is the hexadecimal equivalent. So it's option B. Okay. Uh, this is the final question for today. Number of product terms in the minimized sum of product expression obtained through the following K-map is where D denotes don't care states. You have to simply do a grouping. For this one, since K-map is folded, that's the main concept that you need to remember. This can form one group, right? And then you can form one more group like this. So you will have two terms corresponding to both these groups. It's two. Yeah, that's it for today. If you have doubts, you can ask me now. Otherwise, I will end the session. Huh. For POS, what you have to do? Um you have to group the zeros. So what you could do is, uh, for this zero, see, for that zero, there's no option. You have to include this group, right? And then for this zero, the biggest group you can form is, uh, what is it? You can form a quad here, and the rest of the zeros you can form one big octet. Yeah. So you'll have three terms in POS. Okay. Any other doubts? Okay. No doubts. So I'll stop recording and end the session. Thank you for attending.